Okay, I'm back in it. All right, so this chapter is pretty quick, I think. All right, it's naming, properties, and structure. Then it's a review of acid-base stuff, um, substituent effects on acidity of the carboxylic acid, preparing carboxylic acids, an overview of carboxylic acid reaction, some stuff on nitriles, and then we'll probably skip this stuff on spectroscopy. And um, let's go ahead and pull up this. Okay. All right. All right. So why this chapter? So really, I need to do chapter 21 as well. I was confused. An amide is when a nitrogen is directly bonded to the carbonyl. So then, is acetaldehyde the same as ethanol? I always forget that. This is ethanol. compounds containing the CN functional group are called nitriles and can undergo some chemistry similar to that of CAs. Simple open chain nitriles are named by adding the nitrile as a suffix to the alkane name, while the nitrile carbon numbered C1. So this is 4-methylpentane nitrile. Nitriles can also be named okay. Yo, what's up, Bob? What the fuck is going on? I'm back at school. All right. I mean, kind of off because I have to find a freaking place to live. For next year. Okay, yeah, we're talking about nitriles. Nitriles can also be named as derivatives of carboxylic acids. I can stay at your place. That actually sounds pretty. Okay, so the systematic name is ethane nitrile. That makes way more sense to me. Benzonitrile. What? This is ridiculous. Nitriles can also be named as derivatives of carboxylic acids by replacing the ic acid or oic acid ending with O-nitrile, or by replacing the carboxylic acid ending with carbonitrile. The nitrile carbon atom is attached to C1, but is not itself numbered. 2,2-dimethyl cyclohexane carbon nitrile. Okay, I did these earlier, but fuck yeah. I actually have a lot of work to do. It's kind of we need to cook. You know the chemistry and I know the business. Do you know the business, Bob? Come on. Do you know the business? Alright, so C, 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 C. I also don't know the chemistry, so if you don't know the business and I don't know the chemistry, how well is this thing gonna work? 1, 2, 3, 4, 5. Wait, 1, 2, 3, 4, 5. This is gonna be 2,4-dimethyl pentane nitrile. So here's the carboxylic acid. So C1, 2, 3, 4, 5. So this is going to be 4-bromo-pentanoic acid. Did you actually sell moonshine? No, I know it's a Breaking Bad reference. I know. Dude, I love that show, man. I want to rewatch it. It's so good. So 1, 2, 3, 4, 5. So this is going to be 2-ethyl pentanoic acid, right? Okay, so 6. So I'm going to say it's hex 4N 1, 2, 3, 4 X4N oic acid. That's the one I'm not exactly sure about. Okay, 1, 2, 3, 4, 5. This one's easy. This is just gonna be. Wait, did I already do this one? Oh wait. Oh wait, I did this one accidentally as A. A is just 1, 2, 3, 4. It's just gonna be 3-methyl butanoic acid. Dude, that's crazy. That's actually wild. Damn, what did you guys ferment? What was the. And how did you distill? How did you distill? Is it a. Well, are you allowed to distill in Poland or in Ukraine? Wait, 3-methyl butanoic acid. Okay, so that's A, 3-methyl butanoic acid. So F cis 1, 3 cyclopentane. And when it's attached to the ring, you just add dicarboxylic acid onto it, right? All right, let me check my answers. Okay, 3-methyl-butanoic acid. B, 4-bromopentanoic acid. C, 2-ethyl pentanoic acid. D, they called it Z, but I said, oh yeah, cis. I didn't, or Z. Okay, cis or Z. 4-hexenoic acid. And then E, 2,4-dimethyl nitrile. Then here, cis 1,3-cyclopentane dicarboxylic acid. Okay, pretty simple. Yeah, just sugar. Yeah, it's illegal. Makes sense. It's illegal here too, but one of the like district courts or so, I don't actually know how this thing works, but whatever, like someone's challenging it, so they're trying to legalize home distillation. Oh wait, you said at least for sale. I think it's illegal no matter what for in America. Let's just bang this out. I mean, actually, I know how to do these. I'm not gonna go through this. These are boring because I already read through this. All right, structure and property of carboxylic acid. Carboxylic acids are similar in some respects to both ketones and alcohols. Like ketones, the carboxyl carbon is sp2 hybridized, and the carboxylic acid groups are therefore planar. How do they measure bond angles? That's one thing I never. Like, how do you know that? Like alcohols, carboxylic acids are strongly associated because of hydrogen bonding. Most carboxylic acids exist as cyclic dimers held together by two hydrogen bonds. This strong hydrogen bonding has a noticeable effect on boiling points, making carboxylic acids boil far less easily than their corresponding alcohols. Acetic acid, for instance, has a boiling point of about 118 degrees versus 78 for ethanol. The most obvious property of carboxylic acids is implied by their name. Carboxylic acids. Yeah, I'm not really a drinker either. I don't really like to drink. The most obvious property of carboxylic acids is they're acidic. They therefore react with bases like sodium hydroxide and sodium bicarbonate to give metal carboxylate salts RCO2 minus M plus. Carboxylic acids with more than 6 carbons are only slightly soluble in water. That makes sense. But alkali metal salts of carboxylic acids are often highly water soluble. It's often possible to purify an acid by extracting its salt into aqueous base. And then reacidifying and extracting the pure acid back into organic solvent. Yeah, I've done that lab before. Other Bronsted-Lowry acids, like other Bronsted-Lowry acids, carboxylic acids dissociate slightly in dilute aqueous solution to give H3O plus and the corresponding carboxylate anions. The extent of dissociation is given by the Ka. All right, so here's a little reference of what Kas and pKas are. All right, bro. See you. Yeah, I might be here. I might have to go off because I gotta do this housing search. It's kind of I got a lot of shit to do, man. But yeah, I'll probably be on. I prefer doing the science. A list of Ka values for carboxylic acids. So for most Ks, they're approximately 10 to the minus 4, 10 to the minus 5. Acetic acid has a pKa of about 4. So the thing to remember here is always that the lower the pKa, the stronger the acid. And that's just a nature of the minus log. So really high pKa's are weak. So something like ethanol really doesn't dissociate. But something like trifluoroacetic acid is quite strong. Although much weaker than mineral acids, carboxylic acids are nevertheless much stronger acids than alcohols and phenols. The Ka of ethanol for it is 10 to the minus 16, making it a weaker acid than acetic acid by a factor of 10 to the 11. Why are carboxylic acids so much more acidic than alcohols, even though they both contain OH groups? An alcohol dissociates to give an alkoxide ion, in which the negative charge is localized on a single electronegative atom. A carboxylic acid, however, gives a carboxylate ion, in which the negative charge is delocalized over 2 equivalent oxygen atoms. In resonance terms, a carboxylate ion is a stabilized resonance hybrid of 2 equivalent structures. Since the carboxylate ion is more stable than an alkoxide ion, it is lower in energy and more favored in the dissociation equilibrium. Yeah, so this is good. See, it's basically symmetric. An alkoxide ion has its charge localized on one oxygen atom and is less stable, while carboxylate ion has the charge spread equally over both oxygens and is therefore more stable. Experimental evidence for the equivalence of the two carboxylate oxygens comes from X-ray crystallographic studies on sodium formate. Both carbon-oxygen bonds are equal in length, and they're in between the single and double bond. An electrostatic potential map shows how the charge is spread equally. I'm not going to do the problems for this chapter because it's really just a review. But the answer, yeah. All right, 20.3, biological acids and the Henderson-Hasselbalch equation. In acidic solution at low pH, a carboxylic acid is completely undissociated and exists entirely as RCOH. Wait. Yeah, that's just a bug. In basic solution at high pH, a carboxylic acid is completely dissociated and exists entirely as RCO2-, which is the carboxylate anion. In living cells, however, the pH is neither acidic nor basic, but is instead buffered to nearly neutral. Yeah, what the fuck is up with that? So this should be 7.3 to 7.4. In what form then do carboxylic acids exist inside of cells? The question is an important one for understanding the acid catalysts so often found in biological reactions. If the pKa of a given acid if the pKa value of a given acid and the pH of the medium are known, the percentages of dissociated and undissociated forms can be calculated using Henderson-Hasselbalch. All right. Hello, can I ask a doubt? What do you want, man? What's up? What does that even mean? All right. Please reply. This equation says that the log of the concentration of the... Yeah, I mean, we know what it means. I'm not going to go over Henderson-Hasselbalch. If you don't know it, you're in trouble. Yeah. Okay. I'm from, what country am I from? Let's see. Okay. All right, so we're not gonna do the problems. You can go and apply the formula. It's pretty straightforward. Substituent effects on acidity. The listing of pKa values shown previously indicates that there are substantial differences in acidity from one Ca to another. For example, trifluoroacetic acid with a Ka of 0.59 is 33,000 times as strong as acetic acid. How can we account for such differences? Yeah, I guessed that. I'm also from India. All right. I'm in India right now. Because the dissociation of a Ca is an equilibrium process, any factor that stabilizes the carboxylate anion relative to undissociated carboxylic acid will drive the equilibrium toward increased dissociation and result in increased acidity. For instance, 3 electron withdrawing fluorine atoms delocalize the negative charge in the trifluoroacetate anion, thereby stabilizing the ion and increasing the acidity of trifluoroacetate or trifluoroacetic acid. You don't think I am? Okay. You're just going to have to believe me. In the same way, glycolic acid is stronger than acetic acid because of the electron withdrawing effect of the electronegative oxygen atom. So here we have acetic acid, glycolic acid, trifluoroacetic acid. Because inductive effects operate through sigma bonds and are dependent on distance, the effect of halogen substitution decreases as the substituent moves farther from the carboxyl. Thus, 2-chlorobutanoic acid, as you move this carbon down the line, you increase in pKa. Substituent effects on acidity are also found in substituted benzoic acids. We said during the discussion of electrophilic aromatic substitution that substituents on the aromatic ring strongly affect reactivity. Aromatic rings with electron donating groups are activated towards further electrophilic substitution. Oh, I'm getting a phone call. I am back. I am back. It's pretty funny, actually. Okay, enough messing around. Oh, wait, you're back. You're still here. Stinky. I'm not stinky. What the hell? Okay, we're back. During the discussion of electro, so I think in electro, I really have to review this chapter because I actually don't really get this stuff. But my understanding was that when donating groups donate density into the ring, that the ring itself is then more prone to act as a nucleophile, right? That has to be what it is. There's no other option. Aromatic rings with electron donating groups are activated towards further electrophilic substitution, and aromatic rings with electron withdrawing groups are deactivated. Exactly the same effects can be observed on the acidity of substituted benzoics. All right, so we can see here that if you have a nitro group here, so this would be para-nitrobenzoic acid, right? Let's see if we can get that right. So 4-nitrobenzoic. Okay, and this is extremely acidic because it's a deactivating group, meaning that it's an electron withdrawing group. And so it's pulling density away, so then really the lone pair from a dissociated carboxylate could then resonance stabilize within the ring. But something like a methoxy destabilizes the carboxylate ion. All right. So yeah, here we go. We have paramethoxy benzoic acid, and it's pushing density here. Benzoic acid, and then paranitrobenzoic acid. It's much easier to measure the acidity of a substituted benzoic acid than it is to determine the relative reactivity of an aromatic ring towards electrophilic substitution. The correlation between the two effects is useful for predicting reactivity. If we want to know the effect of a certain substituent on electrophilic, we can simply find the acidity of the corresponding benzoic acid. All right, that's cool. All right, here's where it's new. I haven't really done this part yet. Let's briefly review some of the methods for preparing carboxylic acids that we've seen in previous chapters. Oxidation of a substituted alkyl benzene with potassium permanganate gives a substituted benzoic acid. I don't remember that. That's pretty interesting. Both primary and secondary alkyl groups can be oxidized with tertiary. Okay, that's one good reaction. Why did this stop? All right. All right. Oxidation of a primary alcohol or an aldehyde yields a Ca. Right. So we can do this. So this is formation. Oh yeah, no, it has to be a primary alcohol. So primary alcohol with DNP. Okay. Hydrolysis of nitriles. Carboxylic acids can be prepared from nitriles on heating with aqueous acid or base. Carboxylic acids can be prepared from nitriles on heating with aqueous acid or base by a mechanism that we'll discuss later. Since nitriles themselves are usually made by SN2 reaction of a primary or secondary alkyl halide with Cn minus. The two-step sequence of cyanide displacement followed by nitrile hydrolysis is a good way to make a Ca from an alkyl halide. Oh, that's cool. Okay, so note that the product acid, this is an SN2. Note that the product acid Oh yeah. Notice that the dude, I am out of it today. I gotta get some ice water or something. Notice that the product has one more carbon than the starting alkyl halide. One example occurs in a commercial route for the synthesis of the non-steroidal anti-inflammatory. Oh, cool, ibuprofen. Here we go. All right, so we start with an alkyl halide. We add sodium cyanide. We get this nitrile, and then we add base, and then acid. Okay, so we need to learn the mechanism of this. But so this is ibuprofen. It's how do you let's look. This stereochemistry. What am I looking for? I want to know the name. Where's the IUPAC name? It's insane that there isn't like chemistry tooling is so bad. Like, why isn't there like a nice thing to understand? Like, you type in a name and it helps you understand the name. All right, so let's pull up the name here. So the name is 2. Okay, so wait. 4. 2-methylpropyl. That makes sense. Phenyl. Oh wait. 4 2-methylpropyl phenyl propanoic acid. Okay. So ibuprofen is. But what is up with the 2 here? Oh, because that's indicating the position on the propanoic acid. Oh, that's freaky, actually. That's weird. So it's 2, 4, 2 methyl propyl phenyl propanoic acid. It's always nice to go through a chemical that actually has some utility. I feel like nobody ever talks about, like, we're just talking about stuff without any regards to, like, what, like, is this molecule interesting? Is it cool? Like, why are we looking at this molecule in particular? In any case, this is really interesting. So we can synthesize ibuprofen, but you know what? Like, what's the toxicity of sodium cyanide? Carboxylation of Grignard reagents. And why is cyanide so poisonous? Is it just because it's an amazing nucleophile that it just basically reacts with a bunch of stuff? Is it just reactive? I guess is what I'm trying to say. So like if you spill it on yourself, like are you screwed? Oh wow, this is getting into biology I don't know. Dude, I watched this movie recently called Opus, and in it there's a bottle called that says potassium sodium cyanide in it. And it's like potassium sodium cyanide. This doesn't even make any sense. Bro, Opus potassium sodium cyanide. There's a someone must have caught this. Opus movie? It was actually a pretty good movie until this happened. Dude, wait, what? That's so random. This drove me fucking nuts when I saw this thing. I'm not gonna be able to find it. Wait. Wait, with the prop? Potassium sodium cyanide. You can't really make that out, but they're selling the prop for $250. Should I buy this prop just because it's so stupid? This is so funny, man. That is hella funny, dude. Is that the only photo? Oh, wait, here we go. There we go! No, but see... Okay, wait. We've gotten to the bottom of it. Wait, potassium is misspelled? No, it's not. What are you talking about? That would be a stone too far. All right, we got to the bottom of it. It's a little bit stupid, but it's not like anyway. All right, carboxylation of Grignard reagents. Another method for preparing carboxylic acids is by reaction of a Grignard reagent with carbon dioxide. Yeah, okay, so another way we can do it is as previously noted, there are no Grignard reagents inside living cells, but there are other types of stabilized carbanions that are often carboxylated. One of the initial steps in fatty acid biosynthesis, for instance, involves the formation of a carbanion from acetyl CoA, followed by carboxylation to yield malonyl CoA. Does that really happen? That's pretty cool. How would you prepare phenylacetic acid from benzyl bromide? Okay, well, already there, I would just do, if you see this thing, we just treat it with cyanide. Or yeah, actually, if it's BR, you could also make a Grignard out of it. Okay, that's pretty cool. Should I do this problem? I'm gonna do these problems because these are actually fun. I like synthesis stuff. All right, so we have what? T-butyl group, then and then a C. Oh wait, I think it's just that. Okay, so there's 5 carbons. 1, 2, 3, 4, 5. So we want this from uh, T chloro T butane. What's up, Bob? All right, so I think what I'm gonna do is if I react this just with NaCN, then I'm gonna get this CN group, and then I react this CN with. Well, actually, they didn't really go over the mechanism, but you just add acid apparently. And apparently, acid reduces or oxidizes the nitrile to a carboxylic acid. They didn't really explain that though. Oh yeah, because they're gonna go over it. Okay. Yeah, chemistry of nitriles. All right. You're thinking about buying what? Ethereum? I don't know if I told you, but I don't really care about trading, but I was very interested in understanding the. I'm not really like but I was like interested in. Let me see. I'm not gonna pull up the code right now, but I was having Codex build me something that like looked at 3 venues for cryptocurrency exchange, and I was just running a basic detector that looked at all cycles of currency pairs to look for arbitrage opportunities. And it was actually pretty fun and illustrating experience because the thing is, at first you're like, oh my god, there's all of these profitable trades. That then you do two things. One, you ask the question, how long before these trades get tamped out, and then also, what if I include the exchange's fee structure into the pricing of the, because no transaction is frictionless. There's always some cost to doing the trade. And so, anyways, that's pretty cool. Making big money. I always thought finance and economics was really interesting. It seems like a very fun thing to do. Maybe not just like day trading, like that doesn't sound that fun to me, but like finance seems pretty cool. Okay, reactions of carboxylic acids, an overview. We commented earlier in this chapter that carboxylic acids are similar in some respects to both alcohols and ketones. Like alcohols, they can be deprotonated to give anions, which are good nucleophiles in SN2 reactions. Like ketones, undergo addition of nucleophiles to the carbonyl group. However, carboxylic acids also undergo other reactions characteristic of neither alls or ones. Here's some of the reactions. All right, so I'll probably put some spare Uber Eats money. Dude, that's funny. I want to understand. I spent a while trying to understand these things called forwards, which or basically, I would like to know more about derivatives. You know, uh, contracts, exchangeable contracts in which their value is derived based on something else. So like, like a contract that says you and I will exchange, like we sign a contract to exchange, you give me 100,000 euros or whatever, 10 euros in a year, and I'll give you $10 in a year. And forwards, all of the exchange happens at the expiry date. But in futures, futures do this weird thing called mark to market, where like they update their like you're actually trading part of it based on a market price every day. And then options, I never even looked into options because that seems like really complicated. Okay, let's look at this. So we have HCCOOH. And oh yeah, did you get in on Micron before it blew up, bro? Micron fucking rocks now. I really should have been paying attention. Let's just. Okay, so we have reduction. So this is reduction is H plus, I think. And so we have CCHHOH. Okay, so we have reduction, where we basically just get rid of the carbonyl. So just get rid of. Then we have nucleophilic acyl substitution. Okay, so that's not making an ester. Well, okay, this is called nucleophilic acyl. Oh wait, I'm getting a phone call. You got for 400, sold it. Damn. Wait, how? Hey, what's up? Bobo. I'm sorry about that. Bobo. Dude, that's a huge profit. Did you get more stocks or did you like how many shares did you get? Like what was your profit? Okay, but I have to leave. I'll be back. I have to eat, but I'm probably gonna be streaming until like midnight because, well, not midnight, but I'll be streaming until like 11:30 because I have a, well, we'll see because I have to do this housing stuff.